infrastructure to support. Closer, better? Okay, sorry. So it's about AI cluster network, kind of infrastructure to support the AI training. Something went wrong, sorry. The connection is down. So I guess I need to just refresh. Sorry, the network is down, so I just need to figure out. Yeah. It seems the network is just down. So.
She logged in with hers, so I need her to come back. We'll see. The internet has been maybe working.
Yeah, I have to be internet. So.
Okay, just give me one time.
Oh, no problem. Yeah.
Yeah, but I need her to log in.
Ah, okay. I don't know why. Maybe
I think
when
the
they
internet-
disable the
Yeah.
alarm and then disable everything.
Yeah.
Okay, great. Yeah, now it works. Yeah. Thank you. Thank you. Seems after they clear the alarm, they clear the network as well. But anyway, let's continue. So it's about the AI cluster network, right? So um, where do we start? So basically, the AI modeling, people know that's developed very fast, right? Since 2010, the computation power required for the AI training actually increased, according to us, 4.2 times every year, While meanwhile, the computing power increase for a single GPU or process unit only increase 1.35 times. So there's a big gap, and the gap actually increase exponentially. That's the reason we need to build a actually large-scale high-performance network to support actually the high-efficient AI training. So to do that, if we look at the efficiency of the computing power or the effective computing power, it's determined by three factors: the power of a single chip, obviously, and the scale of the cluster, and last but not least, the computation efficiency. As a networking guys, we don't do the first part. We only care about the scale of the cluster and the computation efficiency. It's easy to understand. The cluster scale actually determined by the network, right? Network can help to connect hundreds or thousands of the GPU or NPU together to let them work more efficiently. While the computation efficiency, how do we understand that? In fact, if you look at the training, it's basically composed of computation time and communication time. So if we can shrink the communication time, so that actually in return improves the efficiency of the computing. So we will talk about those two things in the next slides. So the first of all is the scale of the cluster, right? How big the scale can be. Um, People can always say the bigger the better, but the problem now is we need to find the balance between the high performance and the low cost. Later on in the slides, you will see that, okay, definitely you can kind of power up more and more processors together, but the cost also comes very high. Um, this is one thing. Topology actually is one of the things. The second thing, of course, once you define topology, the routing system running on top of that is another thing that you need to solve, right? Um, the AI communication actually is the most communication intensive applications that we have seen so far. I give one example. For instance, one GPU may send 10 terabytes of the data in one iteration during training. So that's why we observed in the past years that the ever increasing the bandwidth coming out from single GPU chip, right? And this almost come to the capacity of the switch chip. So we need more and more switch chip, the network, to support the interconnection between different GPUs. According to Professor Thorsten Hofler from ZTH, in a crawl topology, the networking cost, including the switch chip, including the optical module, fibers, etc., accounts up to incredibly 70% of the overall system. For a small cluster, maybe still doable, but it doesn't really scale. So the intention actually is to really look for kind of a balance. While on the other hand, actually the 3D torus or torus topology offers kind of a direct connection between different GPUs without the need of the switch chip. It reduces cost. It's relatively cheap. And it also offers uniform bandwidth in different dimensions. But then the problem there is does not really meet the requirements of AI training, because AI training actually come with specific traffic pattern. It's periodic or nearly periodic, and it's bursty. So the torus topology is not so easy to handle that. So actually, the research community come with the variants of from torus like Hamming mesh, KNS, you can name more, right? But we believe that there's more to do, more to explore in this field. If you look at the AI training, more or less converge to 5 parallelisms: data parallelism, sequence parallelism, tensor, pipeline, and expert parallelism. Each different paradigm come with different traffic volume. So on the right side of the screen, you see a table. We take some typical settings of different paradigms on top of a big model with 2 terabytes actually parameters. And from the simulation, you see that the pipeline paradigm and data paradigm generates the smallest data volume, traffic volume, comes to like 11 to 40 gigabytes. Meanwhile, the tensor paradigm and the sequence paradigm generates extremely large volume, which is almost 40 to 200 times more than the DP and PP. And on top of that, the um, tensor paradigm and the sequence paradigm will further increase in proportion to the model size. So you see that there's clear hierarchy of the traffic volume generated by different paradigm, and we need to design something that's to match that, right? Um, so one of the typical design, probably you today already find, is more a kind of hierarchical AI cluster network system. Typically involves 3 different levels: chip level, rack level, and the cluster level. The chip and the rack level actually what we call it actually is high bandwidth domain. It offers enormous bandwidth, electrically connected, and in the low level, even direct topology without involve too much the switch chipset. So all in all, actually, we want to actually reduce the data movement, reduce the latency, reduce the number of hops, eventually reduce actually the cost. Um, if we actually do proper, we did some simulation in-house with a proper model partitioning, 99% of the traffic can be terminated or can be consumed in the chip and the rack level, which left only 1% going out of the rack and then goes through the optical links, what we call it in the cluster level, to the other no, cluster level, yeah, to from one cluster to another cluster. So on the top level, basically, we use one layer of the switch, direct topology like Dragonfly, Dragonfly Plus. You probably heard about this. We also have draft in IETF, and we also use the OCS to enable the topology engineering to support different training tasks running on top of the same infrastructure. So we have the topology. On top of that, we also need a routing system. You may say that, okay, the routing system, IETF already developed BGP or IGP, a lot of routing system. But I would argue that here inside the, for the AI training inside the data center, we need high performance routing system. So as I said, we have a direct topology, direct link from GPUs, one after another, right? 3D torus, like things. So for that, actually, every GPU or every NPU acts as a small mini switch. And of course, we want to make most of the resources for the computation rather than for the switching. So we need to design a very efficient and simple forwarding and routing system for each chipset to avoid consume too much of the precious GPU resources. So high performance routing and lookup table is needed here. And on top of that, because of a direct topology, there was a lot of non-shorted paths, unequal cost paths, right? And we need to make maximum use of that in order to support, actually reduce the flow computation time and support the training. How do we do that? It's also a challenge. And once there's something happens, we probably heard during this week. I heard from AIDC side meeting. I heard from HP one side meeting, and also some talks from RGGWG. People worried about the failure of the training, right? They're evolved with high percentage of the fails. So once something fails, how do we recover? We need to have a fast recovery to actually avoid the further delay of the overall training job. Last but not least, actually, we need to guarantee that the whole over network is deadlock free. But if we look at the existing routing systems, the longest prefix matching, the host-based routing, dimensional ordered routing, or minimum non-minimum routing, are typically running on the existing like cloud topology, Taurus, and Dragonfly, etc., cannot meet all of those requirements. So there, I believe the IETF community has the expertise to look into this domain and try to find um, kind of better solutions for to to meet all those requirements, right? Then we come to the second part of the equation, computing efficiency. We have two ways to solve that. The first is actually very obvious one is reduce the communication time to make it more more optimal. So here actually we adopt the network computing and the memory co-design methodology to explore three areas. One is collective communication, number two, load balancing, and the transport protocol. The second way to solve this is more integrate the network memory and the computation design. I mean, more integrated in terms of on top of the five parallelism I just introduced in previous slides. We want to do a bit more. Can we actually find more optimized the parallelism mechanism? And can we do the proactive data movement? Why so? Because everyone heard about the memory war, right? The AI training needs a lot of memory to store the data, and memory has certain limits. So in that case, they have to really push the data from the tier one to tier two to even further memories. And then the idea basically is you can push towards out, but when you need it, can we actually prefetch the data just before your calculation? So that once you, during your calculation, your data is always on the highest or closest proximity. And on top of that, there was also the in-depth fusion of the network computation and memory. So the first thing is collective communication algorithm. This is the most common things in AI training, right? Give an example of all reduce. Actually, it's the most common collective operation happens in the AI training. So if we look at the duration of the all reduce, it's determined by three factors. The number one is step of the communication or number of rounds, right? You need to run that collective communication. Number two is the latency. And number three actually is the throughput. So basically the volume of the data divided by the bandwidth. To optimize that, we need to minimize the steps of the communication and minimize the communication traffic. Meanwhile, maximize the bandwidth. So if you look at today, the widely used the all reduced method is, for instance, the ring, or another one is half doubling. Ring is a very straightforward one. So if you have n nodes to run the ring, then each node send the data to the next one for one round, and then you need to actually circulate the data to all the nodes in such a way that you need n minus one steps to finish this kind of or reduce calculation, which obviously as the number of nodes increases, the latency actually increases as well. It's not ideal. That's why people come out with the doubling, halving and the doubling mechanism, which kind of solve that problem because the number of the round of the communication reduced to log n. But meanwhile, if the number of nodes is not power of two, then it has problem of the underutilization of the bandwidth. So there, in our lab, actually, we come out with some new algorithms on based on the classical P2P short algorithm. Basically, we prove that via what we call NB algorithm, it can really produce the optimal configurations and settings. At least we prove that in the factory or core architecture, we can get the optimal result. We haven't verified in the Taurus or other topology yet. We are working on that. Since I'm not expert there, so I will not give you too much detail. But in case you are interested in this kind of algorithm, just drop me a message and I will connect to you to the experts from our lab. The second thing is load balancing. Well, yesterday, if I remember well, in the AIDC meeting, Peter from NVIDIA talked a lot about the load balancing. He said the AI networking is pretty much the load balancing. People spend a lot of effort to optimize that. Why that? Because, for instance, in the claw topology, we use the hash algorithm to make the load balancing. That's quite common. But in AI settings, the traffic pattern changes. The most of the traffic come from a small number of elephant flows. So if you still use the hash algorithm hashing, then what we call hash polarization happens, and which will reduce the effective bandwidth from 30 to 50% according to our simulation. So we need to find a way. And if we have the direct topology like a torus or others, as I mentioned before, there's enormous unequal cost paths. And how do we make massive use of that is also the challenge actually posed into load balancing. So we adopt actually the network computing co-design methodology. So from one side, once we have the AI model, we can derive a lot of AI traffic characteristics because you have the model, you know how do we split the model, and from that you can get a lot of information of potential AI traffic there. On the other hand, we know the topology, right? Well, we not only know the physical topology, but also the virtual ones if we virtualize the network. So when you put two things together, we develop some tool set, what we call NetMind. So to create a optimal configuration, not only for the load balancing configuration, but also the modeling participation and the node assignment. So we made some kind of simulation that via that tool, we can reach the multipass throughputs 98% of the bandwidth and increase the training performance by 20%. Transport protocol, this is definitely the IETF thing, right? We need to actually to improve the transmission efficiency. People actually research on that a lot, both from academia part and also industry part. For the past years, almost for each SICOM conference, I do see one or two papers talking about transport related stuff, either CC or other mechanisms. Next week we'll be in Sydney. I guess there will be similar things, topics will be discussed again. From industrial, probably you heard about the Ultra Ethernet Consortium. They have been working on a new transport called UET, Ultra Ethernet Transport, right? The specification most probably will be ready in the Q3 this year. And there, they also spend a lot of efforts to find a best transportation mechanism to support AI training. So largely, it boils down to two things. One is whether it should be lossless or lossy. Traditionally, in the data center, it's lossless, and we use evening bands to support lossless transmission. It works well. But the problem we see that the buffer size actually is in proportion to the bandwidth and distance, especially when the overall system increase. You need high bandwidth. Maybe you also need long distance. In that case, the buffer size will be the nightmare. It will cost extremely high, and there was a lot of problem coming with that. On another part, people talk about lossy transmission, right? But then there you have to handle the reordering, retransmission in a proper way without delaying too much. Because there, for instance, UET is go for the lossy solution direction. But there it's actually impacted by two things. One is the slowness of the feedback signal. You always need to wait for the ARTT or at least one RTT, right, for the feedback. And secondly, the feedback you receive might not be so accurate because a lot of things credit based or latent based on certain estimation. So whether go for the losses or lossy is a open question. People need to figure out. Another thing is the throughput and the FCT, right? So we know that, for instance, TCP has a slow start problem. There's enormous solution to try to solve that. Um, Here, I think we have a lot of research have been done in the past. But then for the AI, in the context of AI, we need to see that once the model is determined, once the paradigm is determined, we have the pre-knowledge. We have a pre-knowledge of AI traffic characteristics. With that knowledge, probably we can design some better way to control the sending window in such to avoid the congestion while make maximum use of existing resources. Um, uh, I will not go too deep into the network computation memory integration because it's less IETF relevant. Roughly, it means in three directions. One of the thing is, can we create a new paradigm, a new the paradigm on top of what I mentioned, the five data tensor, etc., right? But by taking into account about the memory size, taking into account of the network condition. So we did some preliminary research there as well. And the second part is what I mentioned before, the proactive data movement, right? What do we call it? The data prefetching. Um, we know that when you need the data, probably you have to fetch from the far distance. The current practice basically is if you really need to fetch from far distance, you just recalculate them, right? But recalculating them consume extra resources and might not be ideal. So for us, basically, we need to look at the modeling, look at from systematic view, which data should be moved out and which data should be prefetched before the computation. Last but not least, the in-depth fusion of the network computation and the memory. As illustrated on top, that we kind of disassembled each step, each big computation step, each big communication step into smaller parts. I can give one example, for instance, for the communication. You want to send a bunch of data from A to B. Then you disassemble this, okay, you prepare that in the sockets, you send to the NIC, and from NIC you send out. You send out maybe into 3 hops. For each hop, you just disassemble everything, and then you start to look at, okay, should I do this in this sequential? Can I do this in a better order, right? Can I combine the that element from the previous step? If we combine that together, maybe we can have better efficiency. So there are a bunch of colleagues from Beijing actually working on that topic. But anyway, as I said, those are the less relevant to the IETF, so I will skip that. So the next two slides actually is linked with the side meeting we are going to do in this afternoon from 5 to 6:30. It's about cross DC supporting for the AI training. Why cross DC? Also yesterday get verified with our sort. A single DC has its own limit. Number one limitation is power. Yesterday I heard that nowadays one GPU consume 1 kilowatt, and then a typical data center can support like 50 megawatts, and then you can calculate how many GPU you can support in one site. It's very simple calculation. And on top of that, the complexity, cost, space, cooling, they are all boils down to say a kind of a single cluster cannot scale unlimited. So the size will be limited. And on top of that, we argue that how many data center will build only for AI training. In the future, probably it will be cloud computing, AI training hosted in one place. So in that case, you need to support multiple services. Resource will be fragmented, will be virtualized. And in that case, how do you actually group the kind of rest of the resource together to support the very efficient training is another question to be answered. Last but not least, due to the GDPR, we all know that the data cannot move freely from one side to another. Sometimes data has to stay locally. So in that case, the single DC actually has certain limits. Well, then we say, okay, can we build multiple across multiple DCs? We definitely can. But then it comes with new problems. That's across different DCs. Then you have different resources. They are not distributed evenly, and the different DC may be equipped with different heterogeneous devices. Even in the same DC now, if you look at the new generation come only after half a year after the previous generation, you can imagine in one data center, you will have different kind of GPUs with different capabilities. And then how do we actually, people talk about the virtualization, right? You need to virtualize them, and you need to anticipate their capability and then make the new generation work with old generation. And there were also kind of a multi-task I already mentioned. So it comes with different challenges. The long distance transportation, federal learning, topology of final communication, etc., etc. I will not dive into detail. If you are interested in it, as I said, this afternoon from 5 to 6:30, in the room of the Prince of Wales, Oxford, we will organize this a side meeting. So you're more than welcome to join us to discuss about that part. And we believe it is quite relevant to the IETF because we pinpoint like CCWG, TAWG, Auto, etc. are quite relevant to that. So then comes to my last slides, try to summarize. So basically the AI training poses significant challenges to the computing infrastructure and the networking. To address those challenges, we need a holistic view or holistic approach innovation. So the things we need to take to explore basically is topology, routing system, collective communication, load balancing, transport, and the in-depth integration of the network computing and memory. Except number 6, all these 5, I believe, related to IETF. So IETF plays a important role in above fields, and we hope that we can collaborate, we can leverage our intelligence in the IETF community, collaborate together on the future development of the AI cluster network. Okay, that's about it. Thank you very much. I don't know if you have questions. Yeah, please.
Hi, Jean-François. Gerald, In some of the slides, you've been discussing about this tight integration between computing and the network topology itself and how they will be communicating to each other. Do you have any concerns about what would be the consequences from the collapsing of that stack?
Um, you mean the concerns about the message flowing, or what kind of
Yeah,
concern? So we
because
believe,
essentially the way the stacks are typically designed is so that layers don't really know what's happening on the other ones. And what you seem to be proposing is that the lower layers have an understanding about the type of information that is being transmitted and possibly even the content that is being transmitted, which is sort of antagonistic to what we've been designing in TCP/IP
yeah,
for the past decade. So I'm a bit concerned about what would be the environments in which you would see that applied and what could be the side consequences you can imagine.
yeah, this is actually a very good question. So currently, the current practice basically does not have this problem because they typically buy equipment from one vendor, right? But in the future, if you start to buy equipment from different vendors, indeed, this becomes a issue. That's why I believe we need IETF to standardize the interface, standardize the information model passing through different layers, so that we know what the information you receive from bottom or from top means, right? So this is definitely important. Well, meanwhile, at this stage, we are doing research. We assume this information can be interpreted correctly, but in the future, I agree with you that this need to be standardized.
Okay, thank you.
This is Paul Sung from SKQ in Korea. Uh, uh, yeah, very nice talk. So I have a question. You mentioned the inter data center, some AI sporting. The question is, okay, energy consumption and other cooling system inter DC is, I think, a reasonable approach. The problem is some computation point of view, the task should be some decentralized, also merging and also synchronized. So do you have some idea in how to synchronize the result?
Yeah.
So
Yeah.
how to communicate? So
Very good question.
yeah.
So one of the initial ideas is coming from the five parallelism. In one of the slides, I indicate that the data parallelism and the, if I'm not wrong, pipeline parallelism, they generate the least data volume, right?
Mhm.
So we should put those parallelism actually across different data centers. Why? Because the DCI, the data center DCI bandwidth is much smaller than the bandwidth inside DC. So looking at the hierarchical feature of different parallelism, and we need to actually design our overall system to really match that. So
Mm.
one of the practice we have been doing is we just split the data into different data centers. So the data parallelism are performed. Pipeline parallelism can also be performed there, but definitely it's not a good idea if you want to apply sequence parallelism across different DCs.
Okay. So the other things you mentioned some privacy data, certain data should be some not shared because of so especially the medical data or something like that. So do you consider some other the federated learning or split learning something like that? So
Yeah,
yeah.
we consider about the federal learning. Basically, if the data cannot be shared, you probably can share some features.
Mm,
You can share something has been working on, not
mm,
really the raw data. So due to
mm.
the limitation.
Okay, I see. Okay, thank you. Yeah.
Yeah, you're welcome. Okay, so if there are no more questions, I guess you're all finished lunch. So in case you have more questions later on, feel free to drop me a message, email, whatever, so that we can discuss more in depth. Yeah, thank you.
I have a question. I do want to. So, do you envision any other law or regulatory framework that applies to AI apply to this? The network, like GDPR that has been or to